So you've heard of Schrödinger's equation, but what about its integral form using Green's functions? And in this video, we'll jump into how this approach recreates the hydrogen atom's ground state and prove it step by step. Okay, so what is the problem then? This is 10.9 out of chapter 10, and we want to show that the ground state of the hydrogen atom, which is described by equation 4.80, satisfies the integral form of the Schrödinger's equation for the appropriate potential and energy. But note that E is negative, so the wave number K equals I kappa, where kappa is root negative 2 me over h bar. Okay, so why do we care? Well, in this kind of system, it gives us more flexibility and a general way of approaching quantum mechanics problems, particularly when dealing with complex systems, interactions, and potentials. One of the potentials that comes to mind is the Yukawa potential, which has been a great thing in physics, especially in particle physics. So we should keep that in mind as we use new forms because they tend to pop up later when we're not expecting them to. That being said, to use this method, we had to derive a Green's function. That was a whole section in the book. So that is the challenge for you today, is to derive the Green's function that we see in this integral form and see if you can handle it. Now, the thing with Green's functions is they're used all the time in PDEs and ODEs because they're a great tool, but they're not exactly easy to get in terms of knowing where to start, how to start, things like that. So if you can handle getting that done, then you will be ahead of the curve, especially if you've taken a mathematical physics class or something like that. These are very, very useful, and you will see them all the time in Jackson's E&M, so it just makes sense to look into them now. That being said, this is a pretty lengthy question, not necessarily in how many steps we have to do, but in the simplification process. So if you want the PDF to follow along with, feel free to comment and I will send the link to you and then you can download it for your safekeeping. Other than that, if you're curious about the world of science, be sure to subscribe. I post educational content every week to quench your thirst for curiosity. So with that, let's jump into this question. All right, straight to stop number 1. The goal here is to show that the ground state wave function of hydrogen satisfies this form. But to do that, we first need to consider the case where the incoming wave does not exist, i.e. psi naught of r, reference to the vector r itself, is equal to 0. Okay? And additionally, we must incorporate the energy in the wave number. Since the ground state is tied to the Bohr radius, we'll express the wave number and potential in terms of it. Afterwards, we'll simplify the integral equation and determine the necessary steps to do so. So we see that the wave number as given in the problem was k equal I kappa, but from equation 4.71, we know that kappa itself is equal to the Bohr radius times n in the denominator, but since we're in the ground state, n equals 1, so we don't have to worry about that n factor. But this leads us straight to the potential, which was given by 4.52, and this is the Coulombic potential. Note here that we have a bunch of constants relating E squared and then 4 pi epsilon naught 1 over r. There's a whole lot going on there, but again, since we're trying to tie this back to the Bohr radius, multiplying by 1 here allows us to multiply by the definition of the Bohr's radius, where this up top is equal to a, so mathematically we have 1. Upon substituting in equation 4.72, we see that all our constants disappear, and we're left with negative 1 over r times h bar squared over ma. So not too bad, we can clean this up pretty fast. Now from here, what we have to do is plug this into equation 10.67, which is the integral form. So this is the psi naught of the r vector, okay, but we said that the incoming wave was 0, so that goes away. Now we have what we see here, a bunch of constants, m over 2 pi h bar squared. Now here's the piece of resistance, or however you say it, and we see that this is the actual Green's function that we had used or derived initially. Okay, thank you Griffiths for that little mini lecture. But what we see here is that this I and I over A, which the purple came from the wave number, is now going to simplify, and we have I and I, that gives us I squared down here. And then we have the absolute value of r minus r naught in the not expectation, the exponential, and then in the denominator. Then here we have the modified potential. Okay, so now you see why we wanted to tie it back to bore radius, and it's kind of simple now. And then here, this is psi naught of, or psi of r naught, which is equation 4.80, the ground state of the hydrogen atom. So we're trying to prove that this is going to equal that through this Green's function with this potential. And that's going to be really cool. But as you see, we have a plethora of constants with respect to r naught that we can take out front, and that's what we see here. So from the potential, we get a negative h bar squared over ma, and we see that the h bar squared cancel, negative, negative, m and m, get rid of that. We have the normalization factor from the hydrogen atom, and then we have a whole lot of stuff here in the integrand that we need to simplify. So as we see here, that I squared will turn itself into a negative 1, and then we can set up, using geometry, what everything else is. All right, cool. So now that we see that we put all the constants and simplified it out front, we get this cute and compact little integral. The I squared goes to negative, and then we have an A here. So we're done with the setup of this problem per se, but we still have to set up the geometry, which that leads us straight to stop number 2. Okay? And so the next step is to apply some creative geometry and set up this integral in terms of r and r naught. And in this case, setting the r vector along the z0 axis, much like we did in problem 8.9, yields this law of cosine's argument, which I put the diagram in the PDF if you're interested. And so we'll just use that there. We also have the differential element, which is our exact thing that we would expect for a spherical integral in 3D. But note that we're color coding here to where we have r naught squared, and then we have and then dr naught in blue. That will be our r integral. The theta integral will be in green, and then the phi integral will be in purple, just like we had done previously in 8.9. Helps to keep things clear and organized. So if we plug in all our arguments here into the integral form, what we see is that plugging in, making this integral its three-dimensional version, the magnitude r minus r naught, magnitude r minus r naught, the exponential over the radius, and then we see that r naught and one of these r naughts from the differential element cancel, so we're going to continue the simplification act. What we see is that we have nothing here that depends on phi, so we can turn this phi integral into 2 pi, which cancels pretty quickly, thankfully. We want to clean up all the pi's that we can. And then we see that we have the situation where we have the blue integral, the r integral, or r naught integral, and then the theta integral. And it would help us here to evaluate the theta integral first, just like we did in 8.9. And we see here that although it looks really, really clunky, it's actually not as bad as it appears. Meaning that this could be solved with solved with a u-sub, and that's pretty easy to do, all things considered. We just have to be really, really careful. And I purposely color-coded the limits here because in the u-sub, we're going to change the limits and make our way through this problem. So let's see how we do that. So if we let u equal the argument of the exponential, then the derivative du, we have this square root is a 1/2 power, bring the 1/2 down, then you take 1 from the power, so it leads you to a negative 1/2, hence the 1 over square root argument here. Chain rule comes in and we have a negative 2r naught cosine, that cosine goes to sine, and the negatives cancel. The 2 from here and the 1/2 from the square root cancel. So we clean up really nicely to this r naught sine theta d theta from the chain rule. And then if we want to solve for what we have in the integrand itself, we just need to isolate this square root and the sine theta d theta, and that's what we do here. Notice that we get rid of all the other terms to the other side. And now we're in a situation that's really not too bad, all things considered. It's gross, don't get me wrong, but it's not too bad. And now when we evaluate the boundaries, what we observe here is that at pi, the upper limit, cosine of pi gives us negative 1. That negative 1 turns this negative into a positive, and then we have a factorable form of r plus r naught squared, but the square root and square cancel, and that leaves us with a negative 1 over a, r plus r naught. So again, not too bad, but it's still kind of clunky. Similarly, uh, at theta equals 0, cosine of 0 gives us 1. So we do have a factorable form here, but because it's a difference, we need to use the fact that this is an absolute value. And that's what's going to make our lives slightly difficult here later. But nonetheless, we have completed the substitution for this step, and we're good to go. But before we continue, if you're finding value or finding this helpful, don't forget to give it a thumbs up. It helps more curious minds like you discover this content. So with this, let's go to stop 3 and finish this up. Alright, so as promised, stop number 3. Now we have to use the substitution and plug everything in. And this clearly ties up and saves us a lot of headache. Change the bounds, change the bounds. Now we just have e to the u, our new du term. We see that the a and a cancel, beautiful. This r0, that r0, cancel, beautiful. Now we can take all the constants left over here, bring them out front. So we see a r and a negative sign come out front, clean it up. Now we see we just have a basic integral, e to the u, its antiderivative is e to the u. Evaluate at the bounds, and now we see this thing here, upper limit minus lower limit. As we see, the whole goal now is to tidy up this blue integral and set it up such that we can observe what happens with this absolute value. We can do that by distributing this e to the negative r0 over a into both of these terms, split the integral, and then see what happens as we go through the limit process. And let me show you what I mean. So here we have the step where we distributed the exponential on the outside, no problem. And now we split up the integrals. And we have to do this because the bounds here run from 0 to infinity. And if we want this to work, we have to analyze what the behavioral characteristic of each region is due to this absolute value. Okay? And that's what we have to do in defining this piecewise. Okay? And by the rules of absolute values, we see that for r0 less than r, we have a positive here. Okay, because then green r will be bigger and we're left with a positive value. We don't have to worry. But if r0 is greater than green r, then we see that we have to have a negative because then the difference here would be negative. Double negative would make that positive, so we're good to go. But in order to utilize this, we have to split up these bounds into two separate integrals. One from 0 to r, and then one from r to infinity, and that covers everything. And then we have to use these piecewise definitions in order to simplify. So now that we have that, we can go ahead and split up the integral as we see here. Again, we did this in 8.9, so it shouldn't look any more crazy than what we had saw previously. But we note that we can clean up these exponentials pretty darn fast. We have one r0 here, two r0s there. We can combine them. We clean this up. We distribute this 1 over a and everything, and we'll combine like terms or cancel. We should see that this r0 and that r0 cancel because double negative turns that positive, and then they'll cancel. Here, the negative negative cancel, so we should have another combination here. So let's just see how we tidy that up and then evaluate. So as promised, we clean up and combine the 2r0 from the first integral, distribute, clean up the negative signs. We see that we get a negative r0 over a, positive r0 over a, so they cancel. Beautiful, less work for us. Then here we have a negative r0, so they'll combine to a 2 just like that one. The only difference here is that this one was negative, this green r was positive, so now we can be careful when evaluating. But note that the differential is with respect to r0, so re-splitting these expectations up, or not expectations, but the exponentials up, to highlight that we're only after r0 will save us a lot of time. So e to the negative green r over a, green r over a, green r over a. Take them out front because they're constants, all things considered. At this point, you could just take it outside the whole thing, but then you'd have a problem with this positive one, so I just left them integral to integral. And then after that, we know that this is just, you could do a basic u-sub on all of these if you want it. You don't really need to. If I'm multiplying up here, I have to divide by it, so we multiply by the reciprocal, and thus we get a negative a over 2 e to this minus r0 because it's just a constant, evaluate it at the bounds. Same thing here, negative a over 2 e to the negative 2 r0. over A, evaluate from infinity to R. So we get a lot of repetition here in evaluating. Thankfully, infinity and 0, really good friends for the exponentials in terms of simplifying. So let's go ahead and evaluate. Okay, so the overall characteristic here is that we have e to the negative theta, e to the negative infinity here, e to the 0. We know what happens there. Upper limit minus lower limit, so r minus 0. Upper limit minus lower limit, e to the negative infinity. And then here we just have to be careful because that's an r. Okay, so after that, we know that negative infinity leads us to 0. 0 leads us to 1. Simplifies, beautiful. R minus 0 leaves us with r, so we can tag that out front. And negative infinity leads us to 0. And then this just drops down. Now we just simplify up with the signs and make sure everything's okay. This leads us to negative 1. That cancels with that negative out front. Cool. This negative changes that positive to a negative, so we're good there. We combine the exponentials, so we see that green r over a and a factor of 2 here cancel. Beautiful. And as we see here, once we get that cancellation done, we now have a over 2 e to the minus r over a minus a over 2 e to the r minus a. Positive, negative, boom, they cancel. And then what we're left with is something really simple, negative r e to the negative r over a. So the negative out front cancels with that. The green r from way back when cancel with this r. And then we're left with 1 over pi a cubed all in the square root e to the minus r over a, which, by the way, is the ground state of the hydrogen atom. So we have successfully evaluated this Schrödinger's equation in the integral form, and it was not too bad, all things considered. Like most physics problems, once you have the setup there, you can trust the math to be able to take you through it. But if my setup is not right or it's clunky and not cleaned up, this is going to be an arduous process already. That bad setup's going to be more work for you later. All right. Well, it's been a hectic week so far, or I guess 2 weeks with the hurricanes, Francine and Helen. I hope everyone's okay out there and able to have a fun first semester back, or well, I guess fun fall semester. Might not be your first semester back, but nonetheless, physics, math, education will always be there to help us, even when we don't want to do anything. So I think that an appreciation for it is definitely needed. That being said, again, just thank you to everybody who's been supporting and checking up, especially with the hurricanes in the Gulf South. Appreciate all the love and support. None of this is possible without y'all, so thank you, thank you, thank you. And if you find this valuable, please share this with a friend who's also curious about science, and let's grow this learning community together. This doesn't work without a joint effort. Collaborations are seeming to be at an all-time low in education right now, which is really, really upsetting. There's a lot of great, smart people who just don't have someone to bounce ideas off of, which is really weird in the internet age where we're all hyper connected. So hopefully we can continue to grow this community together and push forward and discover something new. Even if it's a new way of teaching, a new way of highlighting interest, there's got to be a way for us to progress somehow. So I hope that in the next 2 or 3 years we can really take that mission and run with it, because I think it's going to have a lot of value for a lot of people. So thank you again for the supporters of this channel. You make this possible, especially all the new patrons that seem to come out of nowhere for this new semester. Appreciate you all. Y'all definitely help a lot and give me great ideas. So I'm looking forward to what's going to happen in the rest of this semester and in the next year, because I think that's where we're going to really take off. As always, thank you for watching, and until next time, stay curious.